printing. Next, we will come about composite materials, specifically thermoset polymer composites, why it is so. Then composite thermal sheets. So that is why I started with space. I am working on space and rocketry composites currently and collaborating with Advanced System Laboratory, DRDO, Hyderabad. And we generate composite shields for any space vehicles which will withstand more than 1200 degrees centigrade. So, you can see that. So these are some of the basics which I don't want to. I take the material where the properties changes with respect to direction, right? You have a tensor called, thermal conductivity tensor. So Kx, Kxx, Kxy. So that means your thermal conductivity of the material, it varies because non-homogeneous porous nature of the material. Okay. So likewise. So here what happens, since it's a layer by layer addition of making the product, what will happen? Indirectly what you are doing, you are making the properties are uniform through the laying direction. So that is one of the very, very important. And you have more mechanical strength between layer to layer because it's not bulk made, whereas we are layer by layer addition. If I can make somehow the plastics have better interfacial bonding, which means the bonding between the two layers, if you can bring out, then it will be a superior material compared to the conventional material. And why this additive manufacturing is important in composite thermal sheets? When I said earlier, when we make some composite thermal sheets for space and rocketry capsules. So you see that slide is there. This is fine, no problem. This is also fine. This is fine. So you can see this slide. So I'll put it simply in simple words. So it may be very little complex to go through. That's fine. See, surface is there. It is introduced with lot of thermal stress, lot of physical stress, mechanical stress. What will happen to the surface material first of all? The surface temperature rises to, say, 700, 800, 1200 likewise. What will happen to the material which is made up of? So obviously, thermally degrade and recession of the material comes, which means with that, all the force, the material is carried out. Okay? So if you have even metal, if it is there, pure metal, it will be carried out with the friction, drag, whatever the stress that is getting created, the material will decrease. That means the thickness of the component will keep on decreasing. So if it decreases, the heat penetration happens. As like Kalpana problem, since one tile fall out, heat penetrated and it made it to plastic. Right? But here you have to have safeguard this one with such a simpler composite material. So first, generally they have in the history, carbon phenolic composite materials were used as composite thermal shields for high temperature applications in earlier days, till Kalpana Chawla came into existence, right? Why it is done is, when this material goes for high temperature environment, it undergoes pyrolysis reaction. That means, since it's a polymer, right, carbon fiber is based on carbon, all the thermoset are based on carbon, hydrogen, oxygen chains. When it goes reaction, when the temperature disintegrates the polymer chains, you always come as carbon dioxide, water, and so on. At the end, all this hydrogen goes, oxygen goes, you will come up with metal carbides or carbides only. Carbon only present. But only carbon is present, right? It goes higher recession. Only carbon is present with thin layer like carbide, carbon nanotubes, carbon sheets, it get formed. But when the velocity of high flow, it will fall off. That means the tiles will degrade, thermally degrade very easily. And generally, these are sacrificial material. It's not the complete productive material. Why am I saying it is just a sacrificial material means we let the material to corrode during the process. We let the material to get it lost. By once it is get away from the earth atmosphere, then the capsule is free of any such kind of incidents. So until it passes, this material should sacrifice itself so that it will safeguard the inner material. But still, the erosion rate is very higher, such that sometimes the heat get penetrate very faster. So to avoid that one, people in recent days, last 20 years, people added lot of metal nanomaterials. Metal nanomaterials like titanium, zirconia, silica, for the thermal stability of the material. But now, when I add some material, that ablation mechanism or the heat, what kind of reaction that is happening, that also changes. So there is one improvement in the material rather than producing just a carbon in the combustion process, pyrolysis process. First of all, carbon will form due to the integration of the polymer material. Then this carbon, what it is made to react with the metal oxide nanofilters. So when it gets reacted with this pure carbon at higher temperatures like 1200 degrees centigrade, when get reacted with the metal nanofillers, you will get metal carbides, which is very, very stable material, thermal stable material. Then even if it is not reacted, you will have metal oxide like SiO2, ZrO2. These materials also thermally very, very stable. But another advantage comes when that carbon is getting formed, it will make a melt and it will make metal carbide as well as the metal oxides make a protective layer. Further heat penetration will be arrested within that. So less recession as well as better production happens when you use metal oxide nanofillers. So this is the mechanism that is happening. But one another problem is there. Generally, when the people design these kind of thermal shields, they design to 300% over design. 300, not just 100%, because after this Kalpana Chawla problem, you have to ensure the safety first. So we go for more than 300%. But what is the disadvantage of going over design? Not only cost, weight of the vehicle. Because after it passes or during the path of trajectory, even if I reduce 1 kg, it saves me multiple energy. This tank, fuel tank will be reduced, right? Size of the fuel tank. That also add weight. Weight is the important thing when it goes to space. Okay? So weight of the capsule, not men or anything else. Right. So when you reduce, but when you go for 300% factor of safety, obviously you are adding more weight to the capsule so that the fuel tank will be more. So everything get increased. So what we proposed to the DST is that we can have such a optimized design with respect to 3D printing, right? And with the factor of safety maximum 150%, not 300%. But it can be done because every time I cannot do experiments and I cannot prove. So I should do experiments, I should develop some simulation tools, I should say that this is perfectly working. So it is a combinatorial approach. You develop the thermal shield, composite thermal shield by computational way as well as experimental way. But when I have to do computations, I should have the proper physical properties, right? So physical property in the sense I should carry out what is my thermal conductivity, what is my specific heat, what is density, Ct, mu, K. So that properties I should have. That is easier when the material is homogeneous. Since we are adding fillers, what will happen? When I add fillers to resin, the fillers will be distributed in the resin matrices. I cannot assure that it will be uniformly distributed. So if it is uniformly not distributed uniformly, what will happen? All the physical properties are very much scattered, right? And another very important parameter here, what's the range of the temperature that parameters has to be studied? If I have to take thermal conductivity not at room temperature, because the application temperature is 1200 to 3200 minimum. Can we have any equipment to measure thermal conductivity from the range of 1200 degree to 3200 degrees centigrade? It's very difficult. Because if I have to study to that temperature, what the equipment should be made up of? The material equipment I should have, that equipment should withstand 500 degrees centigrade. What material is there? If I can able to make that material which can withstand 5200 degrees centigrade, straightly I can use that one in the space vehicle itself. So there are a lot of practical problems. Okay. And now comes to the existence of this additive manufacturing. So what we proposed is that when I prepare a composite thermal shields using 3D printing, right? Since it's a layer by layer process, I will mix the resin, I will distribute these fibers into the resin using ultrasonification. I remove all the air interrupt by vacuum bagging. Then I put it into the syringe, DIO, direct ink writing method. Put that material. I just very simple layers, small thin layers will be added. And the bed will be kept at certain temperature. So there is like process optimization of 3D printing process, because the resin has to cure, but it should not completely cure. So there is always a certain consistency required, because you need to build up the material platform, okay, in the thickness direction. If it is not curing properly, what will happen? Resin is generally a viscous liquid. When the material is filled up, somewhat viscosity will be increased. But when I lay down, some degree of cure is expected, unless otherwise you attain certain degree of curing. When you build the next second layer, it will flatten. It will not build up in the thickness direction. Okay? So there are a lot of optimizations required when I go for 3D printing. But when I successfully 3D print this composite thermal tail, what are the advantages? Since I orient to certain direction, I could say that I could at least, I can have a uniform physical property in the layered direction. That's a concept, it has been proposed, it is accepted. We got a project of 30.5 lakhs from TSD, CRG, core research grant. Okay? So I hope you know what is the mechanism, that's called ablation. Right, so you can able to see that the heat shield of it. It's like the old technique. Now we have space shuttles, but still growing countries like us in aerospace department, like we still follow the same thing. So some kind of vessel, it will fall into the ocean. But whereas if you see from US, you will have a space shuttle. Okay, so you will have like aircraft structures, it will directly, the astronauts will be laid down with the aircraft structures. Whereas we are still trying with taking some vessel outside the Earth's atmosphere and bringing back. That exercise are getting started already. Okay, but we will use that one only. You might have seen in older this thing, some parachutes used to bring that vessel and it fall into the ocean. So that's kind of olden, you know, even in Gravity movie also, the last part of this one will be there. And if you rightly see that, when it fall into the ocean, water boils, you will find some of water get evaporated at the surface. You can understand what will be the surface temperature of the metal vessel. There are some motivations. So people have not done with the 3D printable composite thermal shield as of now. So this is not yet published, but we have filed the patent for this. 3D printing coupled with photo curing to manufacture complex composite parts of nanofill thermosetting resins. I take relaxation that you know about thermoset resins because we all from chemical background. So it replaces cost-intensive conventional electrically induced heat source with photo-initiated curing. This comes with a low-cost methodology itself, because when you go for thermoset resins, you have to use electric conductive process, which is little costlier compared to the photo-initiated. Photo-initiated, you know that photo-cure resins cure faster. We say that activation energy for any kind of reaction. So activation energy for the photo-cure reaction, because as you know, the light itself cures the material. Whereas thermoset means you should apply more than 50 degrees, 60 degrees centigrade, where you need rod heaters or some kind of heating element, which needs a lot of energy. So we try to reduce with respect to photo-cure resins itself. So next one is even distribution constituent fractions within the composite parts, stepwise direction oriented thin film. That's what I was saying. We are indirectly creating a material which can be isotropic in nature. So next one, direction and enhanced property, same thing. 3D printing technology to develop composite parts in all major applications. So one another very important point I missed out here, why we have gone for 3D printing, because the component what you make for any rocketry or space vehicle will be a geometrically stringent geometry, dimensionally stringent. If I have to make 1 mm thickness, there is no other room. You have to make 1 mm, and that is very much possible when you go with 3D printing. It's fine. Okay, so main objective is to develop the composite thermal shields. First of all, the sub-objective, maybe I should know the formulation. Then I have to optimize the 3D printing process. Then I have to characterize whatever I have developed, whether it is suitable for thermal shield applications. These are sub-objectives. So this is like a schematic representation of how to formulate and how to 3D print. So as I said, we used dual cure. That means we mixed two different resins, which can be light cured as well as temperature cured. Okay, so we used some kind of epoxy into the phenolic resin. Phenolic resin produces a lot of char. It is very much proven candidate for thermal insulation purposes, but we added epoxy because the metal nanoparticles will have a glue between. It is called interpenetrating network. It will act as interpenetrating network for the phenolic resin as well as the metal nanofillers or whatever particular matter you are filling. So obviously you can use UV curing for light curing part, or you can use high temperature plate for curing the material. So this is the pictorial representation of how we are preparing the resin, the formulation. So this has been already dealt with. So these are the characterization for the resins. So when I fix the material, what are the minimum characterizations you have to know? So it is proportional to the degree of cure. So obviously you can ask what is degree of cure. It is nothing but the equivalent term of conversion, reaction conversion. Hope you understand what is conversion. Obviously many of us are chemical engineers. So it is equivalent term. So maybe I can go in detail also. So just for the information. So in a classical chemical engineering thing, so how will your rate of the reaction is done? You have rate expression in terms of X, right? So you will get X. How will you find out X? So X means like the concentration profiles you will do. So how the reactant concentration decreases as a function of time during the reaction will be dealt Then after that, with respect to different temperature I do, from that I can, with respect to first order, second order, pseudo first order, zeroth order, I try to fit the things and try to find out what rate law it is fixing in. After finding that rate law, what I do, I'll find out so activation energy as well as frequency factor. Activation energy is nothing but, so if it is lesser, we can say that the reaction is more spontaneous. If it is more, we can say that we have to supply energy to make the reaction happen. That's it. And frequency factor is nothing but it's a collision factor. It's of many factors included, majorly collisions. What we believe from classical theory, the collisions of molecules makes the reaction. So that factor is directly proportional with respect to frequency factor. So as like in polymers, particularly thermosetting polymer, the curing is nothing but the reaction, what it is happening. It cannot be directly as like countered like classical chemical conversion reacts. So whereas it depends upon the exothermic. So how much exothermic heat? Since the curing is exothermic in nature, the amount of heat evolved will help us how much curing, how much polymerization process happened, right? So here most of the time depend upon the curing. So there is a physical change as well as a chemical change. Physical change in the sense thermosetting will go, first of all it's a viscous liquid. Due to curing it will go to gel state, then it goes to rigid solid state. This is a physical change. It can be evaluated using viscosity measurement. That is one thing. The curing is nothing but it is exothermic in nature. As I said, the degree of cure or degree of conversion depend upon how much exotherm it get away. It will be characterized through a thermal characterization technique, differential scanning calorimeter. This tells you how to do the characterization part. Actually, if you are interested, you can ask. Okay, so I'm skipping this slide. It's little, you have to do the experiments. After that, you have to do the interpretations as well as some kind of modeling. You have to do it so that you will get, you have to get the kinetics model, activation energy, and so on. So that will give you a complete picture of how the resin can be handled for the processing. Like for an example, I have to choose the temperature to cure the resin. So what will be the temperature? You may not aware it of. But when I do the kinetics part, time, temperature, cure process window can be developed, that can be implemented so as to cure resin to certain degree of cure. Okay, this is characterization part. Obviously, in any of the material, if it is novelly done, chemical composition has to be characterized, morphology has to be characterized, and application oriented. In this case, it is application oriented, means thermal shield application. That means you have to do this thermal erosion test, okay, thermal stability test using TGA, thermal gravimetric analysis, right? So obviously mechanical strength is required, like how far when the resin is whether it will bear some kind of mechanical load or not, that also has to be tested. So those are the characterization techniques you have to adopt to evaluate the material supremacy. So here in this work, composite thermal shield work, we used phenolic resin, nanosilica, boron nitrate. Nanosilica and boron nitrate. Nanosilica will give you structural integrity along with thermal stability. Boron nitrate also, it will withstand more than 2000 degrees centigrade very easily. So both are the proven candidate which will be applicable for high temperature applications. So as I said, we use little epoxy to enhance the properties of a boron dissolved phenolic resin. And that resin is only available with DRDO. We may not be able to get it outside. Due to research purpose, we obtain and we have characterized. So when you go down the line, there will be photoinitiator to initiate the curing reaction. So there is another cross-linker for the epoxy is glyceryl methyl and there is 3D printer. It looks very smaller, but it makes the wonder. So it can build volume of 20 centimeter, 20 centimeter, 20 centimeter, but you can do in that simple machine itself. Thermoplastic can be 3D printed, photo cure resins may be 3D printed, and thermoset resins can be 3D printed, not only the neat polymer, but also with nano-filled polymer. Okay? So all the things can be done in that one single machine. It is purchased out of the project only. So you can able to see that. So first phenol resin is there. We add nano fillers, and we go to the 3D printer. You can able to see that how it is direct ink writing 3D printer. So with the needle, we put layer by layer addition, and you can make some build volume of the composite product. Thermal shield is there. Then it has to be post cured. Probably it will be only. It also requires some optimization. Some minimal optimization on curing has been done with respect to application of the bed temperature. Then after that, it has to be post cured in the oven. That will be your final cure. So this comes some of the optimization. So we have, this is not yet published, actually it is patented already. So probably I may not able to give the complete detail, and I request you not to reproduce anywhere. It's my humble request. So you can see that we have developed a lot more formulations with further characterizations. With optimization, we could understand that what will be the optimal chemical composition, like what will be the composition of how much percentage of phenolic resin, how much filler loading, right, how much percentage of epoxy resin has to be taken, so that we have optimized, and along with that we tried to compare with the printability. So that is also important. I can mix anything, probably the mixing thing will give you enhanced properties, enhanced whatever property we expect it may match, but the thing is that if it is not 3D printable, again I cannot get uniform physical properties, direction oriented properties. So that is why it should go with both the things. The composition also to be varied along with the 3D printing process. Process parameters also has to be optimized. So this has more than 2 years work. So we relentlessly work day and night with the various formulations, and then we come up with one optimized formulation. Okay, so this gives you better understanding. So this is merely how to optimize the 3D printability. So some of the examples come, the resin flow like liquid. Right, I mixed with certain proportions. It doesn't have enough viscosity. When that direct ink writing machine works out, it's like a needle, the fluid flowing through a needle. So the major expectation from 3D printing process that since you are using a lot of particulate matters within the resin, it should have a continuous flow first of all. It should not have cracks. Not only during printing phase, you should not cracks when you get cured. When it gets cured, we know that lot of, in the resin itself, we add, if you are a chemist, you may be well aware, we add lot of organics to make the resin diluent, like the viscosity will be as low as possible. We'll have some organic salts, for example styrene. So styrene will be added to any raw plastics or raw thermoset resins so as to reduce the viscosity of them, so that the processability will get enhanced. But when the temperature is applied, the styrene will vaporize easily, because it's if I'm not wrong, boiling point will be 70 degree, 80 degree. So if it is even sometime at 50 degree itself, it vaporizes, it comes out. It's not good for health, as well as if it comes out, what will happen? There will be some cracks formed. So you should have the printing without cracks. That's what you have to do. So that is also has to be optimized. So merging layers. So what it says, if the layers are getting merged, that means the platform building is not correct. The physical consistency, viscosity is not good enough, and the curing also not happening to the appreciable percentage such that it will make a rigid structure, so that it will be built layer by layer. That is also happening. So when you go with the step-by-step process, you can see that from inconsistent flow, see first the resin is flowing like liquid, the next one is the merging of the layers because it's not substantial, curing is happening. So next one, inconsistent flow because when the material is coming out of the needle, it is not continuous itself. But when with the trial and error, you can able to see that a consistent flow is happening, and you are able to print. You will see the printed specimens later on. Again, I print. So I optimize the printed parameters. I printed. Some of the printing happened, but when I go for the curing, so further post curing, I could see that volatiles are getting evaporated, right? So in that way, lot of cracks happened. It is on post curing. That also not good. So I should have a proper thing. What I did, I increased the bed temperature, plate temperature to. First initially we tried with 40 degree, 50 degree, then I went to 80 degree. With 80 degree you can say that you have a very nice composite thermal sheet getting formed. So there are some glimpses of how the sheets are printed. So at 80 degrees centigrade we could have very nice structural integrity, and we know what viscosity also has to be characterized, depend upon how much force has to be applied on the syringe. So this is rheological study. So generally rheological study, you want to know what will be the shear rate it is required. That has to be implemented in the syringe so that the upper arm of the 3D printer will move, so that you will have a consistency in the viscosity so that it can be printed very easily. So generally, as we know that we conduct viscosity in two modes. One is constant shear rate and variable shear rate. Constant shear rate will give you whether the viscosity is varying with respect to time, and then varying shear rate will give you whether it is Newtonian or non-Newtonian in nature. So obviously with respect to time, with the different, it is giving a shear thinning behavior. That means when the shear is getting increased, viscosity becomes diluted. And it has been, with respect to different filler concentration, it has been studied. And we have to characterize photo cure. So it is differential scanning calorimetry can be obtained anywhere. You will get that equipment very easily. But photocalorimetry is not that easy to get. So it may be like 4 to 5 places only it is there in India. It is nothing but, so you keep the resin under photo cure resin under light, certain light intensity. You see that how much polymerization happening. So that will be taken care by photocalorimetry. Okay? So it has been done with photocalorimetry because as phenolic resin is majorly of photo resin. So with the nano fillers, how this, because when I fill some of the nano fillers, it hinders the curing process. So area under the curve will be the rate of it is the reaction value, heat of reaction, right? The area under the curve. If it is more, we can see that the reaction happened completely, right? And the cross link density will be. So mechanical strength we try to find. So there is always some kind of trade-off you require, like when I look for thermal performance, mechanical performance will not be there, because if I add more fillers to it, so it will add some time until certain percentages mechanical strength may be enhanced, but after some time, because you have to bind each and every particle within the resin medium, if it is not happening, mechanical strength will come down. So we have done, these are the tests you have to do: mechanical strength, structural strength, compressive strength, and with the different formulations we have done, and we found these 4 compositions are much better than the other combination study. That's why I just put it as an example. And in this thermogrametric material, like you apply temperature from say room temperature to 1000 degrees centigrade, and I wanted to see that how the mass loss is happening within the material. It has two things. One is like you have two phases. So one is the resin is degrading, the other one is filler starts degrading. Okay. So when it is more than 50%, see, whatever temperature you apply, 50% of material is getting retained. It is not thermally degraded. That means we know that this is thermally stable ablative material. We know that carbon might have obtained due to the temperature. That carbon react with the metal and it makes metal carbide, which is more stable for the temperature of 1000 degrees centigrade. That's what 50% material is retained in the pan, which says that this is also an example, the confirmatory that we are making metal carbide or metal oxide within the combustion pyrolysis reaction.
Okay.
So this is very important test when it comes to this application composite thermal shield, where the material is introduced to the high velocity flame. The tip of the flame will go more than 1200 degrees centigrade, and you can even increase or decrease the velocity of the flame. So that is, the material will be introduced to the flame, and few things are observed. One is what will be the back wall temperature. So back wall temperature, in the sense the temperature at the back side of the specimen will be continuously monitored, and we'll see that at what time how much temperature is increased. Okay? So when the material is degraded due to high velocity flame, obviously there will be increase in the back wall, increase in the temperature of the back wall. So very importantly, what you have to notice here, erosion rate. So how erosion rate? After completion of the test, I will take the sample out, I clean out, all the carbonate again, and I take the weight, initial weight and the final weight. I take it as what is the amount of material is eroded for 1 minute, and it will be divided by 60 minutes, 60 seconds, it will be erosion rate. Millimeter, it is eroded per second. So back wall temperature will be, is that after 1 minute of testing to high velocity flame, so what will be the final temperature? Final at the end of 1th minute, what will be the temperature recorded at the, because this material will be into the existence for only 1 minute of flight. 1 minute of flighting time. Accordingly, we have to extrapolate the thicknesses, right, to design the optimal thermal shields. So you can see that, so the back wall temperature got reduced to 160 degrees centigrade to 36 degrees centigrade, but the tip temperature is more than 1500 degrees centigrade. So we made 10 mm of the material, and we see that it is the penetration of heat till to only 36 degree by formulations, optimized formulations, and the erosion rate 0.327 to 0.110 millimeter per second. You may say that this magnitude is very smaller, but when you take the complete figure of the capsule, this is a tremendous achievement that the erosion rate has been brought down to 1/3. Okay. So there are major conclusions. What I conclude majorly is that we could able to identify, optimize the formulation first of all. Then we could able to successfully 3D print, and we demonstrate the composite thermal shield will work well, and we have tested in ASL, Advanced System Laboratory, DRDO also. Probably we may try to implement, and that too they are planning to buy a full-fledged 3D printer for this purpose. So it is funded by the project development of 3D printable composite thermal sheets, and from core research grant DST sir. At this moment I thank the funder. So there are some ongoing sponsored projects and some of the patents. So not only related to this, but this thing, and we have generated full-fledged laboratory resources for composite 3D printing as well as for composite manufacturing. I'm basically working on 3D printing of polymers, then advanced composite materials, then process modeling, simulation and optimization. Also, we have developed one simulation tool, optimization tool for that is copyrighted also for composite processing. So even a person with a low level of knowledge can operate that algorithm very easily. And there are certain composite manufacturing molding techniques that is also created, the facilities are created. These are my students. So without them, the work is not at all possible, and we work on multiple different, not only the composite machines. So presently there are 11 ongoing PhD scholars, one postdoc, and already 3 guided as PA, and currently there are 2 MTech students, and in my career almost 20 MTech students passed out. I will graduated out. Thank you. I'll be very happy if there is any queries. Any queries, please? Anything if you could not understand or if you want to know, I'll be very happy to address. Yes, please. Yes. Come again, please. That's what. Right. Yeah, I will say. See, when there is pyrolization happens. See, all the carbon will convert it into carbon dioxide. That pyrolizing gases will come out. That's for sure. But when I say that with the metal oxides, when I use metal oxides and the metal, what happens? It makes metal carbide or metal oxide. That will first comes like a melt, but it become rigid solid. That material also, the carbide material, metal carbide material, say boron carbide. If you search in the internet, it will withstand more than 1600 to 2000 degrees centigrade very easy. It has the structural integrity as well as thermal stability. Right? And another important thing is that if you see where this friction, maximum surface temperature increase to that temperature is like when you go out of earth crust. That means it is more than, if I'm not wrong, after 50 to 250 kilometers, and with the rocket speed, vehicle speed, it will pass us within few minutes. So once it is get out of earth crust, there won't be any problem at all. There is no space, and there's space, but there is no earth atmosphere. So there you doesn't have much resistance. So when you go out, when you go into the earth atmosphere, there is the problem. In that phase only you need these kind of material. You can have metal also, but what is the problem in the metal? Weight. Weight is the problem. Earlier we used to have alloy. Alloy also will have a lot more weight. So now this whatever US use spacecrafts, it's more of this composite thermal sheets. If you see correctly, at the bottom of or whatever place it is more experiencing more friction, the material looks like black. And every time they change this composite tiles. So only the outer space will be changed. So we tried with commercial also, but since we have the collaboration from DRDO, we will get the best grade out of that. Because boron nitrate and all, we can buy from general vendor. Problem is that the quality. So if it is lab grade, it may not be good enough. So we want to have a superior grade. So whatever resin and the filler, so we take from them. So the co-PA is from ASL only. So he helped us to get. And thermal erosion tester we created right now just 1 month before only we installed in our lab only. Before and all we used to do it there from there end only. At this moment I have to thank my co-collaborator, scientist F. Siddiq sir. Like he is one of my PhD scholar too. So right now he is doing as a part-time under me. So if there is any question, I'll be happy to answer. Otherwise, I'll wind up. Okay. Thank you for your patient hearing. I hope you get few things out of it. That itself, the success of the presentation. Thank you once again.
Thank you so much, sir, for your inspiring words. Now, to express our heartfelt appreciation, we would like to felicitate our esteemed speaker. May I kindly invite Professor Rajesh Katiyar, sir, Dr. A.K. Rathore, sir, and Dr. Sastry, sir, to present a token of gratitude to our speaker.
चलो मैं बिजी हूँ। अच्छा काम कर रहा हूँ।
Thank you so much, sirs. So now we will proceed with our next lecture sessions. I would like to call Nandini Chaudhary, who will be introducing our next esteemed speaker, Mr. Vishwas Deshpande, sir.
कहीं ऐसी जगह फटेगा।
Thank you, Kirti. Mr. Vishwas Deshpande sir is a chemical engineer with an MTech from the Indian Institute of Technology, Kanpur. He brings 3 decades of experience in process engineering, EPC project execution, and engineering management in hydrocarbons and related projects in refinery. Mr. Deshpande sir began his professional career with Larsen and Turbo Limited, where he worked for a decade as senior manager, project execution for refinery. Later, he joined Reliance Industries Limited, where he served as vice president in project engineering management, contributing to the development and execution of mega projects in refineries. He has also worked internationally with MS Kellogg Brown and Rodd, AMCPTE, Alcobar, Saudi Arabia, gaining valuable global experience in large-scale engineering projects. Currently, he is working as a freelance process consultant and independent advisor and has published many papers in national and international journals on process engineering and energy-related retrofit, revamp, greenfield and brownfield projects. So, I would kindly request sir to come on the stage and address the gathering.
Good afternoon, everybody. At the outset, let me express my sincere thanks to the Department of Chemical Engineering for giving me the opportunity to come here and share with you my thoughts on zero liquid discharge. In this context, I'll be talking on the distilled spent wash, how we can link the green finances, carbon credits to the effluent management. I presume that most of you have the fundamental knowledge of distilled spent wash, so I'll not spend even 1 minute on explaining various items which are related to distilled spent wash. What you see over here, actually India's E20 program is much ahead of it. It was targeted to be over by 2030, but it has achieved this target 5 years before time. So not only that, there is a surplus ethanol available, and now IITI is pressing government to push forward the E30 or E35 program much ahead of the schedule. But all this is fine. This cars, etc., they show actually increasing trade with respect to ethanol production. But what really is happening is that with increased ethanol production, it is putting more and more pressure on the effluent that is generated. Needless to say that we are talking here about one of the most complex, recalcitrant, difficult, obdurate and whatnot type of waste. Very difficult to treat, but it's of course it's a challenge for chemical engineers how to deal with it. Yeah, this is the slide actually showing the kind of things which are happening around us. Actually, we can discuss about E20. Let me talk about first April 2026. What's going to happen on this day? On this day, the implementation of E20 will be, E20 will be implemented nationwide. So it's a most important day. Thirdly, now government is planning for 2G type of ethanol. What is meant by this is that whatever crops which are left in the field after cutting the jowar or wheat, or for that matter even the grain and maize, those feedstocks can be also used to manufacture ethanol. And lastly, why we are doing all this? We are doing all this because it is going to increase the income to the farmers. Also, there will be less greenhouse production due to diesel combustion of fuels, and of course, there is less dependence on the imports. So we are going to save a lot of foreign exchange on the oil imports. Okay. Now, anybody who's in the distilled spent wash treatment and disposal will know that the amount of literature around this topic is simply terrific. I mean, I would say a couple of Himalayan type of literature available. Any paper you read, any literature you see, any reference you take, it starts with how difficult this waste problem is, and ends up with saying that how helpless we are as far as its final disposal is concerned, or achieving zero liquid discharge is concerned. However, the research treatment and disposal of wastewaters, distilled spent wash, must continue. First and foremost, it is because this particular waste we talk about, it has got a very high BODs UV, highly acidic in nature, which is about 4 to 4.5. It has got dissolved solids up to 10% concentration. Its COD is to the tune of 1,20,000 milligram per liter. BOD is to the tune of 65,000 milligram per liter. It has got pungent smell, which is disagreeable. It's got a brown color that's related to the atmosphere or the pit at about 45 degrees centigrade, which is actually the outlet temperature of your analyzer column. So, in a nutshell, it is a very complex waste problem to be treated. Secondly, the current technologies have got its own limitation. For the Indian context, there are two technologies which are very popular. One of them is actually the anaerobic digestion, where actually you do the anaerobic digestion of this waste. The second one is actually evaporation incineration, in which you take 10% of solids concentration waste and you concentrate it to 60% and take advantage of the fact that the displaced petrol at 60% of solids concentration will burn of its own once you maintain the pilot flame. The amount of heat energy available is about 7600 kilojoule per kilogram, or let's say 2200 to 2400 kcal per kilogram. So there are two technologies, but the anaerobic digestion is definitely not a foolproof solution because it gives a digestate which is both solid and liquid. The liquid digestate, even you take about 90% treatment efficiency with ED, will render the waste from 65,000 mg per L to close to 4500 mg per L or up to 5000 mg per L, which is still about 5 to at times the specified limit by the IICHE codes for its disposal of the land or for the water. As far as the evaporation, and secondly the solid waste which comes out of the anaerobic digestion is actually a waste that needs to be distributed. Its volume is very large, and so far it is used as a fertilizer or even for landfill. About evaporation incineration, yes, it is the technology which actually gives the total zero liquid discharge, but it's very expensive. So there are the limitations of the current technologies. So research must continue with this particular field. Thirdly, we are talking about actually the circular economy, and also we are talking about resource recovery. So this particular waste, it has got actually the sodium and potassium salts, which can be readily recovered and used as fertilizer. So we have to look at from resource recovery and circular economy point of view. Fourthly, the regulatory norms for treatment and disposal of this distressed pet wash are becoming stringent and stringent. Particularly the CPCB norms, they say that there has to be zero liquid discharge and this will be applicable to distillery. Fifthly, the quantity of water required in the industry is down. They had to optimize their resources. No longer we can think of wasting the water. In fact, technologies which generate the water and conserve the water is appreciated, and actually this is the main focus for most of the people who are with the displaced pet water treatment. And lastly, we are a country where our technology, requirement of our technology may not be suitable for what West is dumping on our third world countries. We have all actually feedstocks, we have our own climatic conditions, and we need to indigenize, we need to have cost-effective technology which actually serves to impart any substitute as an import substitute. For all these 6 prevalent reasons, we must continue doing research into distressed pet wash. Okay, now talking about 2 technologies. Like I said, anaerobic digestion is one of the solutions, but it is not 100%. It will never give the zero liquid discharge. Water digested in the liquid form which comes out, which still is about VOD of almost 5000 mg per liter. So it is definitely not a zero liquid discharge solution. Plus, couple of 2 more slides which I want to show on the anaerobic digestion. These are actually the data which I have collected from various operating plants in India on anaerobic digestion. The anaerobic digestion has got some problem with respect to startups and process stability issues. First is actually the startup process is very long. Second is treatment is inadequate during startup time. Then the intermittent operation plant is not practically feasible. Sometimes you don't need to operate a plant on a continuous basis, but once you stop the plant, restarting the plant is also a big problem. Thirdly, the anaerobic digestion is not a shell-safe type of process. And lastly, there is a lot of yeast carryover which happens in anaerobic digestion. Obviously, actually these are the issues which are listed, and against each issue, there are practical consequences for hygiene faced the plant. They are listed. This is not published anywhere, but this is out of my experience working with plants. The yeast carryover is basically a problem. It creates actually foaming and biomass washout, as mentioned in the last column. Then there are operating issues and mental issues for the anaerobic digestion. First is actually separation of the sludge. This anaerobic digestion results into formation of sludge, and separation of the sludge is often necessary and it's very difficult to remove the sludge. Secondly, since the BOD is getting reduced from 65,000 to 4,500, secondary treatment is essential, and the secondary treatment also is not efficient, and it is actually highly capital intensive as well as energy intensive. Even after secondary treatment, tertiary treatments sometimes have been reported in the literature and they will be practiced by many countries. The sludge volume is very, very high, so except for landfilling, at present it doesn't find much of a use. However, it could be the handle sludge itself and its disposal is a separate activity by itself. The media which is there in the anaerobic digester is prone to fouling very often. So that is true, and its replacement is very expensive. Lastly, during the processing, obnoxious hydrogen sulfide gas is generated, which is toxic in nature. Mind you, this hydrogen sulfide gas, when it goes to the boilers and the tubes, it forms actually sulfuric acid, which corrodes the boiler tubes. And retrofitting those boilers or replacement tubes are also very expensive. So these are some of the operational and maintenance issues with respect to anaerobic digestion. Then there are actually treatment performance and process limitations on anaerobic digestion. First is COD of the waste is reduced to only 65%. Mind you, the COD for this the distilled spent wash is to the tune of 1.25 lakh milligram per liter, and it's 65% reduction. And the final COD could be to the tune of 30,000 milligram per liter. COD is basically our energy, heat energy, which is present to the waste. The BOD reduction is only 85%. So if you start with 65,000 milligram per liter BOD, you will end up with having BOD of almost 6,000 milligram per liter, which is not acceptable to the CPC. Thirdly, the COD of the influent effluent has to be low, so you have to dilute that waste before you put it to the anaerobic digester. And removal of the dissolved solids. This cannot be achieved to the desired level. And removal of the color. So color also is not possible to remove using anaerobic digestion. Coming to the evaporation and desalination process, like I said, this process is the process which actually is very attractive from the point of view of total pollution elimination. What we need to do is we just work the spent wash. Now, prima facie it will look very, very simple, but as I will explain gradually, that it also requires a lot of challenges to be overcome. All of us know that this spent wash has got about 10% dissolved solids concentration, and this is not a unique property. If you start heating this spent wash and bring the dissolved solids concentration to almost 60 to 65%, then if you maintain a pilot flame for this waste will keep on burning by its own. All you require is basically the initial auxiliary fuel to maintain the desired temperature, and once you get the 60% of concentration, it will burn on its own. The energy that is obtained, which is about 2400 kilocalorie per kilogram, which is enough to generate a steam in the boiler. The quantity of steam which is produced, I will say that it meets the sugar factor requirement. Also, it meets the preceding distillation tolerant requirements in the ethanol plant. Also, surplus F4 scheme is available, which you can use for preceding evaporation operation or the distilled spent wash. Not only that, the condensate which is obtained, you can reuse it in the fermentation portion of the distillery. So nothing goes as a waste. Okay. Now the plot that has been shown over here, it shows actually the dissolved solids on the x-axis and the LCD of the spent wash on the y-axis. Okay. So actually, we start heating this wet wash, start increasing this dry solids concentration from 10% onwards. You can see the enthalpy of the heat content keeps on rising, almost linear. So when it comes to a threshold, operating point, that is 65 to 60%, at that point actually it will ignite of its own and will start burning. And you need to maintain the flame only up to that concentration. That one will start burning of its own, give you the desired heat. A very interesting graph that you can see. Actually, what are these dry solids and how it is affecting? There is something called the effect is not solids into the spent wash. The spent wash has got the solids which actually contains sodium and potassium salts, which is actually valuable from the fertilizer point of view. These solids actually they get concentrated, and this concentration of these solids actually consumes energy. So when you start concentrating the spent wash by putting steam, basically the energy is utilized for the solids to get melted. It forms the eutectic. Eutectic is a substance whose melting point is actually lesser than the melting point of either of the pure salts. So these eutectics actually has got a very fluffy mass, and it actually goes to the convection module of the fired inter furnaces and blocks the heat transfer areas. Converting it to total useless. You have to take the shutdown and clean the boiler. But recently, so many new type of boilers are available, particularly developed by Kinetic Technology International, where they are self-clean type of boilers. About that, I'll talk a little bit. But here, actually, you can see that you have something called a trade-off. If you put a steam to actually increase the solids concentration, you are basically releasing the energy which is there with the biological content of that spent water. There is a BOD, you are trying to reduce that and you are trying to release that energy which is in the dissolved form. So it is not that you are consuming energy, you are actually trying to release, because if you can see, the total solids actually is basically it tells you the composition, but the composition of that total solids actually tells you the energy enthalpy content of that spent water. So we have a trade-off. We can see energy content is coming down with a decelerating, and while decelerating actually there is a practical it actually gives out energy at 7600 kcal per kg, where they actually the threshold. Okay. Now there is a very interesting graph which is published by Italian scientist. Let me go back. Okay. So actually it is pretty straightforward. This actually the plot which I had shown. It actually explains the conceptual energy balance for concentrated spent wash evaporation versus energy recovery. So this plot explains the thermodynamics logic for zero liquid discharge. Spent wash is not an energy deficient. It is energy diluted by water. Progressive evaporation upgrades its energy density, and at about 60% dry solids concentration, it becomes net energy positive. This defines the autothermal ignition threshold. Beyond this point, incineration can be sustained with minimal auxiliary fuel. And Venus is a poor fuel itself, but has a good combustion characteristics. Namely, it's a transferable transport flame, the ease of ignition, and ease of automation. Therefore, evaporation without energy loss is stable. But it is actually the energy upgrade just stable, as I explained to you subsequently. The dry solids define the quantity, but the composition defines the combustibility. Here you can see that the solids which are present here, there are the droplets of spent wash. Inside that droplet, actually the sodium and potassium salts are concentrated. It forms a melt, and this melt is basically responsible for slagging. And this slag actually goes and gets deposited on the heat transfer surface of the boilers. Okay, so this molten sodium potassium salt, they consume the energy and they promote slagging. So this graph actually shows the melting behavior of the inorganic salts in the concentrated molasses vinasse during combustion. Temperature from 500 degrees 50 degrees centigrade to almost 900 degrees centigrade. The most critical zone is between 550 to 650 degrees centigrade. Where actually eutectic melting is taking place. So the modern boilers, what they do, they maintain the temperature in the convection module between 550 to 650 degrees centigrade, so that as soon as the eutectics are formed, they get deposited into that region by maintaining that temperature. And whatever fuel comes out, it's like a clean fuel and which could be used for generation of the steam. This is one of the most important slides. During vinasse extraction, dissolved sodium potassium salts concentrate with droplets, forming low melting eutectic phases that consume combustion energy and promotes lagging. Straightforward. Then concentration measures the energy density only if the incremental solids are organic. When salts dominate, deeper concentration merely increases the thermal load without improving the fuel quality. And the figure which I am going to show right now is published in 1981 through Kinetics Technology International, Sweden. What it shows that if the concentration of these salts is not increasing from 5, 10, 15, 20 up to 30% salt, the corresponding corresponding heating value of the spent wash actually comes down. If you look at the 60% of solids, at 0% salt concentration will give you about 2500 kcal per kg energy, whereas the same waste with about 30% salt will give something like 600 kcal per kg, which is almost 30% reduction into the heating value of the coal fuel. This graph is available with in this particular journal, which I have taken from this journal. Okay. Excuse me. Excuse me. Actually, thoughts get lost. It is a distraction, please. What we are talking today, like the conference theme is actually sustainability, recirculation and whatnot. This is the theme of the conference. It's not that we did not know what this was, it already existed. If you look at this 1981 paper published in South African journal, it shows the circulation from starts with bagasse, 100 tons of bagasse to sugar, cane, from cane to sugar cane juice to sugar, and then bagasse to phosphorus and fuel. Then sugar, it generates molasses to ethanol to stillage, that is the vinasse. It's also called as tender or spent wash. Now spent wash to evaporation incineration. You recover the energy. From energy you generate steam. That steam will generate power, and the power is put back to the distillery, sugar factory, wherever else, whether it is required. The condensate which is generated is used as a water. So you are recycling water, and finally the ash that you get after burning this spent wash, it is used as a fertilizer. So whatever you are taking from Mother Earth is returned back to Mother Earth. So it's not that we did not know, it existed. Today, 2026, we are talking about this, but it existed in 1981. What was lacking was basically the policy and the scale. Today we have all these things. So we can go ahead with whole. Okay. Now suddenly what has changed? It already existed. Like we know that there was many methods which are available for treatment and disposal of spent wash. Like primary methods, secondary methods, tertiary methods, even polishing methods, evaporation, incineration, putting it on the land straight where we use this waste as the fertilizer. All this was very well known. But what has changed? What was there earlier? What has changed? What has changed fundamentally is that now there was a global awareness sometimes in 1970, 71, where actually various nations came in, UN came in, and what they formed actually some kind of strategic goals. All countries they came together from strategic goals because they concern towards the environment. Perhaps this concern did not exist before 1980s, but it started coming up. As a consequence, during various years, actually there is a global evolution of the green finance. What started as a mere concept, after in Tokyo, Geneva conference, actually there is a formation of the green fund. And all of us know this development. Even now, India hosted the G20 and took the lead in the world towards mitigating the issues related to the environment. Okay? So this is the change which has happened. There's on one hand, there's a global awareness towards the environment, deterioration environment, and something needs to be done into that. And secondly, the availability of funds. So these things have changed. So this distillery spent was treatment and disposal, if attacked properly, can meet the strategic development goals, SDGs of UN. This is the goal number 6, goal number 7, goal number 12, and goal number 13. So if you can make a project and position it in such a way that it orients towards the goals, SDGs which are set by UN, you can definitely qualify your project for displacement water disposal. Okay. Now there are what has happened to the codes which are tolerance limits for disposal of spent wash on land as well as on the estuaries or water. So there are the codes actually IS 3306, 3307. These are basic codes for disposal of the wastewater onto the land. Whereas IS 7968 is the code which is used for disposal of the waste into the sewers or on the estuaries or for the irrigation purposes. Here it is important to note that the BOD5 maximum allowable is only 100, is about 500 milligram per liter for the land disposal, and for water disposal about 100. Okay, so as you will see, your AD, your anaerobic digestion is not able to give that kind of a final concentration of BOD5. It is 5,000, so it's about 100 times. So obviously, alone, anaerobic digestion struggles to meet the requirement. Alone, evaporation actually struggles because there is no capital level. Okay, it actually achieves zero liquid discharge because there is no liquid. You get only ash and everything is burnt off. But still, it was not practiced because it's very, very expensive. We need special material to handle this kind of waste. So some trade-off was required. Now, apart from that, now, because of the India's push towards this EBM process, that is the ethanol blending program, EBP program of the Honorable Prime Minister, there are about 380 distilleries all over India, and about 35 new projects are approved and sanctioned, are in the pipeline. Then actually when the higher ethanol production means there is the increased generation of the distillery spent wash, then tightening CPCB norms on the land and water discharge, and now mandatory zero liquid discharge through integrated treatment approaches, and rising global focus on water stewardship and environmental accountability, and lastly expanding green finance ecosystem aligned with the SDGs. This is what I am talking about. You have to align your project with respect to SDGs. So scale brings the responsibility. So what I am saying is that why the province, although we know that the circular economy, what it did exist, it did always exist, but why did not scale? The fundamental reason there actually many reasons. One of them is technology was known, but the incentives were disaligned. I'll give an example. Actually, circular solutions for distillery effluents were known, like I showed in the slide, that African paper which was published. So it was known, but it was known decades ago, but it was not the economics, it was the economics, not the chemistry, which actually dictated actually the adoption. Why it was adopted, it was basically the economic consideration, not the chemistry consideration. Secondly, I'll give a simple example. In 1990 economic comparison in India, if you think about 30 KLPD distillery, investment would be to the tune of 1.5 crore rupees. If you talk about evaporation incineration to achieve ZLD, the investment would be about 4.5 crore rupees. Now what does that mean? For the same capital of 4.5 crore rupees, I can construct 3 more distilleries for the same investment. And these distillery units will be able to beat the profit. It will shorten the profit. Normally distillery makes the profit after 2 years. But if you have 3 more distilleries with the same capacity, it will be 4 divided by 3. So you get faster returns by putting distilleries, 3 more distilleries, instead of putting money into evaporation incineration. Okay, so the thing is actually it was more towards the economics, not because of the chemistry. Chemistry was very old, all of us, we knew that. And the resulting behaviors, actually capacity expansion prioritized over the environmental integration. So nobody wants to do a project, evaporation incineration and mitigating all the general requirement. They would prefer getting a profit and investing more into the distillery project. So capacity expansion prioritized over the environmental integration. Secondly, faster returns, shorter paybacks, and limited accountability. I would say that the distilleries were running, they are running. So accountability, there's issue with respect to accountability. Somebody has to be responsible for putting that kind of waste and spoiling the environment. That was not there. Then environmental costs were externalized to the society. These are the resulting behaviors as a consequence of the investment into a project like this. The key insight is actually the sustainability failed not due to the lack of solutions, but due to absence of financial and governance framework. This distortion is precisely what a modern green funding mechanism are designed to correct. So this kind of a distort is now being corrected through the green finance. The carbon credits, actually, what are the carbon credits? I will not go into definitions, all of us know. It is always based on the emissions avoided compared to an alternative. Right? So this is the carbon credit. The carbon credit eligibility depends upon the baseline scenario and not on the avoided emissions. Okay. Secondly, the methane destruction qualifies because methane is a GHG, which is 100 times, 20 times more damaging than carbon dioxide. Okay. Thirdly, high energy ZLD systems may not, unless integrated with the renewable energy. Traditional ZLD thinking ignores carbon intensity. A system that emits liquid discharge but increases atmospheric carbon may not be environmentally superior. Fundamental things. Now, if zero liquid discharge is the boundary condition, then sustainability is the system's outcome. Right? All of you agree? Fine. Now, while carbon capture and sequestration is technically feasible, its application to decentralized evaporation and incineration systems is currently uneconomically and infrastructurally constrained. Straight away. Therefore, the real engineering challenge is not the sequestration, but optimization of the carbon intensity. This must be noted. Now, if you look at the distillery charter from CPCB, Central Pollution Control Board, they have issued actually a charter which actually talks about 10 different technologies for ZLD. ZLD is a mandate. You have to meet ZLD, no doubt about it. Now, this you can achieve through combination of 2 or 3 technologies or through a single technology, but you have to ensure that you achieve ZLD. Now, aerodization actually removes the major part of BOD, we have seen. and then converts these organics into biogas, which contains 60 to 65% methane, and reduces suspended solids, and process digest it with reduced organic matter. Okay, this is what ET does. But its effect is actually to lower the organic load to downstream system, lower calorific demand in the incinerator, and renewable fuel availability. So obviously next frontier is reducing the carbon intensity. So when the anaerobic digestion removes most of the BOD related material, actually the evaporation section is blessed because it is less foaming material. It is low value of COD for the liquor. Then actually the auxiliary fuel which is required to burn that particular fuel actually gets also reduced, and the steam demand to do the evaporation process also get reduced. So obviously there is an improvement in the system. You need less steam for evaporator. Then the energy balance, carbon intensity, operating cost, they are all automatically get optimized. If you don't have aerobic digestion, the all organics which are dissolved into the spent wash, they go directly to evaporation incineration plant. So there will be high evaporative load, high auxiliary fuel consumption. But with aerobic digestion, part of COD goes to biogas. Then biogas, it goes to boilers, it fires the boilers, generates steam. So it reduces the fossil fuel input. So obviously there will be smaller carbon footprint per kiloliter of pollutants. So what I am proposing over here is, if you have a plant which has got actually anaerobic digestion as one part, and in series of that, you have actually evaporation incineration plant. Then you will achieve zero input. Alone, anaerobic digestion will not give you zero liquid discharge. As we have seen, it will generate BOD is about 5,000 mg per liter. And alone, incinerator was not feasible previously, but now if you are able to align your project in such a way that it aligns with the SDGs of UN, then your project can pass. And then actually the low COD, or rather the low BOD intake is taken to the evaporator incinerator, it produces energy. So after burning the entire waste, what waste you get is converted into fertilizer. So you are able to achieve not only you are able to recover the potassium salts, but recover energy, but also you are able to achieve energy. So what I am proposing is a series of aerobic digestion followed by evaporation system put together and project it in such a way that you are able to qualify this project for green funding by aligning its objective with the SDGs of UN and ask for the funds. These funds were earlier not possible because the cost of evaporation system was extremely high, 5 crore. Nobody would like to invest that much. But now this money is available. It is up to us to take it. But it's very easy to be said and done. It's not that you go to bank and say that give me loan. It's not very easy to say that, okay, I'm putting up a MEE, multiple effect evaporator, in my distillery, and you give me the, they will not give. What you need to prove through a basic engineering design package or through proper design report, DPR, that you are able to achieve a objective which is in line, which align with the objectives of or the SDGs which have been put by you. Like I said, SDG number 6, 7, 12 and 13. If you do that, various agencies like NABARD, IREDA, or these agencies actually, they do the funding, they'll approve your project and you can get a loan and you can put it. After getting green fund also, life is not simple because this is actually accountable. You'll have to really demonstrate that with respect to a particular baseline, you have been able to mitigate the carbon content emission into your system. Okay? So this is what is being proposed. Okay, with this actually I would like to run through a typical case study with you people. very quickly. You start with what is actually 60% of solids. 60% of solids you consider 1 ton of distilled spent wash. So it's about 1000 kilo weight. Obviously, water in it is actually 400 kg and 600 kg of total solids. Out of these total solids, the only organic matter into those solids actually is carbon. Okay, so the total carbon content is about 40-45% of that total of solids. So you have total carbon of 240 kg. Simple calculation. If you take sulfur carbon dioxide production, so you produce about 880 kg of carbon dioxide. So energy from 1 ton of distilled spent wash is 20 kcal per kilogram multiplied by 1000. So it can generate these many calories of the energy. So coal equivalent, if you consider CV of the coal, that's about 4000 kcal per kilogram. So equivalent coal would be about 600 kg. I had taken 4000 kcal per kg because Indian coal is full of ash, so you don't get that kind of energy that you are really looking for. So you are able to equivalent coal will be about 600 kg. Mind you that if you talk about CO2 reduction for anaerobic digestion, no registry for carbon credit will give you credit for those carbon because this is a biogenic carbon dioxide. Like you have taken it from the Mother Earth and returned it back to Mother Earth. So nobody will give credit. But what you need to produce is that the biogas which is generated through anaerobic digestion, it has got 65% methane, which is actually a greenhouse gas. This greenhouse gas is burned so that you are mitigating the methane liability, which is actually 120 times more damaging than carbon dioxide. That you have to protect. And the CO2 that you get by burning this 600 kilograms of 400 kilograms of 240 kilograms of carbon is actually contributing towards the replacement of the fuel. Because there also you are burning the spent wash, you are also generating CO2. But mind you, the energy that you produce is able to replace the coal equivalent to that. So that actually is the net contribution towards energy saving or carbon credit. So this is what actually the calculations say. So in this calculations, I find that net avoided carbon dioxide is almost 1.44 per ton. So carbon credit potential is about 1.44 ton of carbon dioxide per ton of distilled spent wash. If you apply it for 60 kLPD distillery, these calculations, you work out that is almost with annual 330 days of operation, you save about 2.56 lakh tons of, you can get that kind of a credit per carbon dioxide. Straightforward numbers. So the annual emission reduction of 2.56 lakh ton of CO2 equivalent is obtained by comparing baseline scenario, where spent wash would release methane into the atmosphere, or with project scenario where methane is captured through anaerobic digestion and utilized as fuel. The avoidance methane emissions together with fossil fuel displacement of the basis of the carbon credit potential. Okay. Now, what assumptions I made in my calculations are there is no auxiliary fuel which is used. Of course, we will add some CO2. There is no startup fuel used. The boiler efficiency is similar. There is no methane upstream, which hardly is the case. Actually, there is always some CH4 upstream. No additional fuel, fossil energy for evaporation. In reality, the carbon credits will reduce by about 10 to 25% because of these non-idealities, which is fair enough. So, an interesting comparison. A methane avoidance route will give you 67,000 tons of CO2 per year, and coal displacement will give you 2.5 lakh tons of CO2 per year. So coal displacement is nearly 4 times the methane avoidance route. Thus, evaporation and incineration is very attractive from the carbon credit point of view. So this we must always consider a point. I am not advocating that anaerobic digestion is bad. I am not advocating that evaporation incineration is the best. I am not advocating for any of this. What I am putting forth in front of you are the options that if you put this way, it is possible for you to get a zero liquid discharge as well as complete destruction of this waste and uh, free distillery from any kind of waste discharge in future. So that's all I have to share with you. With the last statement that the future distillery will measure success not only in liters of ethanol produced, but also in terms of CO2 avoided for the future. So thank you so much. This is what I would like to ask. Any questions, please? I know I have not been given any pictures, diagrams, because this is all there. Tons and tons of literature is there. I mean, but they all start with how bad this, how damaging waste is, and how we are not able to mitigate it. So I want to avoid all that. There's tons and tons of literature available. Every paper, every article, every journal you open, it starts with the same thing. It gives the properties of spent wash. It tells you they are able to do only this much, but they are not able to further. So somebody has to take a stance and somebody has to say how we can find a path forward. Actually, today I discussed these 20 to 25 minutes, actually a little step in that direction. I am really thankful to you for giving patient hearing and listening to what an abstract what I was doing. Thank you so much. And any questions, please ask me questions.